Okay, so first lab, what we do is microscope use. You all see the microscope right here. We'll get to the structure later on. But first, we need to go over some of the basic knowledge. I need to find a white. Okay, I'll try to do this one to write on the blackboard. So, first thing, microorganism. Okay, we were talking in the lecture, microorganism is too small to see by naked eye. So we need a tool which is called microscope. And most of the microscope, or all of the microscope in this lab, we call it light field microscope. What this means, which means you specimen, the sample will be showing up. The background is bright. So somehow like this. Okay, underneath the microscope, you will have the sample, which is stained or using the dye to manufacture, which is showed up the color, and the background is bright. So we call it bright field microscope, or we say light field, bright field microscope. Okay, so that's the first thing first. Now, microscope, we want to mention several important index, or we say important items, which is you need to learn or you need to know. Obviously, lots of you already know the microscope or has been using in different classes. First thing first, we call the total magnification. So for microscope, obviously, we want to magnify. Because it's too small, so we magnify it. You can see. You use your naked eye, you can see. There is a very simple formula for the total magnification, do the calculation. It is a magnification of ocular lens multiple the magnification of objective lens. So, where is ocular lens? The most expensive piece of a microscope is lens. Ocular lens, obviously, is close to your eye. Objective lens is down here. There is basically 4 objective lens. We're only going to use 2, or barely we can say 3 during the semester. Okay? Ocular lens, the magnification. The microscope word we are using is always 10. Okay, so the bulb is always 10. And the magnification of objective lens could be multiple. Okay, let's say you have a 10x objective lens, the magnification. So, what is the total magnification? Is 10 multiple 10 equal 100. If you are using the magnification of objective lens is 40x, what's the total magnification? It will be 10x multiplied by 40x, then equals 400x. Is that right? If your objective lens is 100x, so what's the total magnification? It will be 10x multiplied by 100x, so equal 1000x. So that's the first thing, is total magnification. Okay, that's a very easy but a very important concept. That's the first thing. Second thing, we want to mention the working distance. So let's just write number 3. The working distance. Okay, what is the working distance? here is lens, objective lens. Okay, we basically have 4. So we're going to draw like that. I have another one right here, and I will draw another one right here. Okay. This is actually a very short one, so we say it's a 4x. You can observe here it is red. The second one is 10x. Then we have a 40x, and we have a 100x. This is objective lens. Okay, now we have a stage. The stage is right here. So I'm going to draw a picture with a stage. Okay, this is stage. What is the working distance? So working distance is the distance between objective lens to the stage. So this is working distance. So you can see the working distance is decreased with increasing of objective lens magnification. Okay, that's a working distance. That's why we're going to talk about working distance. Because we have another concept which is very important we want to mention. It's called oil immersion. So what happened? These light field and bright field microscope, the energy resource is at the back, is at the bottom. It is a light. Okay, so let's say we have these things, we plug it in. Okay, we plug it in, we turn it on, and you see the light. The light is going through at the bottom, so the light I will going to draw like this. Okay, the light is right here. That's a light resource. Okay. Now this area is glass. So we're gonna say this area is glass. Okay, the whole area is glass. This area is air. Is that right? So that's air. That is air. That's air. That's air. How about the objective lens? Of course, it's glass. So that's glass again. Okay, now a very basic physics knowledge. When the light going through a different medium, from glass to the air, then to the glass, what will happen? It's a refraction. So the light going through here, what happened? Like this. Some goes like that. Some goes like this. Some goes like that. Some goes like this. Is that right? There will happen, like refraction will happen. We call light refraction. And this light refraction will be increased with increasing objective lens magnification. So what happened? It will be very fuzzy, which means you cannot see specimen or you target the sample very clearly, you will see if I don't do anything, I use 10x to find the sample, and I switch to 40x, it's a little bit fuzzy. When I switch to 100x, you completely lose the focus. You cannot see it even because of the light reflection. So we have to solve the problem. How we solve the problem? Well, you already know. Everybody knows it. We're going to put one large drop of the oil. That is called oil immersion. What's the function of the oil immersion? Is to remove air gap, reduce, or we say eliminate. It won't completely eliminate. We just say eliminate light refraction. Now why? Because the refraction index of oil equals 1.5. Refraction index of glass equals 1.5. And the refraction index of air equals 1.0. These two are equal. So when you put oil there, which makes the light microscope is a whole system. From glass to oil to glass, their refraction index, all 1.5, is the same. Okay? So this means we tells you what's the function of the oil immersion to remove the air gap. Now, since this is the first class, so we want to make sure everybody understand we are at the same page. We're not going to use 4x the whole semester. I see lots of people go there using this red one to find it. We're not going to do this one. You will see right here, very small, this red one. We don't use it. Okay, if you are using CU friend, CU bench partner, or doing that, tell him you may not listen very well, so don't use that. We will stick to 10x to find the specimen, find your sample. But when you do the observation, you will not see any of the detail, including the morphology, the shape, morphology, the color, and arrangement. You're not going to see very detailed. So we're going to add 1 drop of the oil, switch to 100x to do the observation. 40x, we will be barely use only one section. When we do the pathogenic modes, I will have a very molded bread around the middle of the November. And I have to make it sometimes in October. Make a very molded bread, and by the time middle of the November, we could use 40x and use lactoferrin, the staining. We could see the pathogenic modes. So that's the only time we're going to use the 40x. But most of the time, we're going to stick to 10x, find the specimen, add 1 drop of the oil, do the oil immersion, switch to 100x. Okay, so that's something we want to talk about, is oil immersion. Now, the next one. Remember, we talk about use 10x and 100x. For these type of the microscope, there is a very good characteristic. Now, obviously, what I said, a very good characteristic, is assuming this microscope is good. We call parfocal. What this means? Very simply say, once lens focused, switch between lens, focus, stays. Okay, so what this means, if I use 10x to find the specimen, then I add 1 drop of the oil, and I need to switch to 100x. You only need to do very minimal adjustment. So I will say with very minimal adjustment. Which means, obviously, you are using fine focus. Okay? Okay, right here, we could go back to talk about a microscope structure. But there is a remaining one big thing we haven't mentioned. Okay, this is a light field microscope. $2,000, $5,000, $3,000, depends, different brand. First thing, you need a plug-in. Okay, then turn the light all the way to the end. We'll explain to you why in a second. Okay, now we have a stage. This is called the stage control. And we have this one could move back and forth. This click is for the glass lights, put it there. And the lens we already mentioned, close to your eye, is called ocular lens. And the bottom one right here is objective lens. And we have to do the focus. The focus, we have the 6th knob. This is called coarse focus. And the thin one, which is called fine focus. Whenever you hold a microscope, make sure you hold the arm. Another hand, which is on the back of the bottom of the stage. Okay, so stage and the arm. And also very important, you will find something at the bottom, underneath the condenser. There is something around here. We call iris diagram. This could be control light amount. Okay. If you are put at 4x compared to put at 100x, the amount going through the objective lens is completely different. Obviously, the light will be much larger when the iris diagram put at 100x compared to at 40x. And it's right here, the click is right here. Okay. Now, what's the things we haven't mentioned? We talk about the magnification. And we talk about total magnification. That means how magnified it is. But the key thing here, for the microscope, we could differentiate two very closely attached particles. And we have to differentiate that. So what is that called? Resolution power. This is something important for the microscope. This is called RP, the acronym RP, equals lambda divided by 2 and NA. This formula could be more complicated, related to triangle formula, lots of the math behind it. We just gave you a straightforward, the final concluded formula. Okay, so let's talk about that. What is a lambda? Lambda equals light wavelength. Remember I said when you plug in the light amount, you all the way to the bottom. That is the light wavelength. The light wavelength here is fixed. It is equals 625 nanometer. Okay, and then the 2 is being fixed. Okay, let me double check it. What's the number? Sorry, 650 nanometer. That is 650 nanometer. 650 nanometer. 2 is fixed. Now the question is this NA. What does NA means? This NA means numerical aperture. What is that numerical aperture? If you do the observation, you see this white one, 100x. And then if you look at it carefully, they will say 100x and 100x 1.25. So what happened is, in this lens, you see 100x, so you write OU, so you have a number 1.25. This number is numerical aperture. I always say this is like size of the engine. Like the size of a car engine, and here is the size of the microscope engine. So you can do a calculation. 650 nanometer divided by 2 multiplied by 1.25 equals 650 nanometer divided by 2.5. What you get? 260 nanometer. That equals 0.26 micrometer. Now, why this number is important? Can you guess an average bacteria? Okay, let's say Staphylococcus aureus. We will mention this bacteria a couple of times in the lab. Staphylococcus aureus. What is the average size? The average size equals 0.5 micrometer. The resolution power of the light microscope, what we have today, with oil immersion, this is the one with oil immersion, is 0.25 micrometer. This number is smaller than 0.5 micrometer, which means we could do the clearly observation. Is that clear? But how about a virus? Okay, let's say we had a virus. We're going to draw the virus like that. A virus like that sometimes. So like this. You have a virus. Average size of a virus is like 10 nanometer. That means 0.01 micrometer. Can we do the observation? No. Because the resolution power is larger than the average size of a virus. So basically the virus, we cannot use light field microscope to do the observation. We need using an advanced tool, which is electron analyzed microscope. Because their resolution power is using electron magnets, it's much smaller. By all means, what we say, the resolution power should be the smaller the better. And regarding the formula here, since 2 and the numerical aperture is fixed, which means the wavelength has to be the smaller the better. Is that clear? The smaller the better. So when you turn it on, this has all the way to the back. Lots of people just do like this, right in the middle. Obviously, you cannot do the clear observation. The reason is this light wavelength is not 650 nanometer. It may be 900 nanometer. Okay, so you just want to make sure you understand about these things. So, this is the basic knowledge where we talk about the microscope, the total magnification, the working distance, the oil immersion, the particle, and the resolution power. today's work is very simple. We will do is a mended microscope observation. We're not going to do the dye, so you're going to have two sets. Here is Staphylococcus aureus. So every student will do the observation of Staphylococcus aureus. I only have so many pieces, so you take the turn. Another guy, you will do the observation of the budding yeast. That's a Saccharomyces cerevisiae, which is the yeast used for beer brewing. Okay? Everybody have to watch those two slides and record it on your lab notebook. You can take a picture, you can put it there if you want extra points. I only have so many pieces, so you're going to have to take the turn. Now I want to show you how to use a microscope. Okay, so I want everybody just to come into the front a little bit. So I'll do the observation, practice, a demo for you. Don't bother that camera. I can move the camera a little bit close, but then you can. I can show you how to do it. Okay. I'm moving the camera a little bit close, so I certainly need the oil right here. So when you finish everything right here, remember we have 4x. This is 100x. This is 10x and 40x. We don't use these two in the first couple of labs. We're only going to do the 10x and the very long one, which is 100x. So let's see. We're going to do a demo using Staphylococcus aureus. You need to find the one which is better. This has been there for 10 years. Since I'm at WVU, I bought it. So it's $5 one piece, so don't block it. Okay, so first of all, we want to put it in the middle. Now how to use it? You're going to be all the way, go down, okay? So you go up, go up, go up, go up, go up. So first of all, do this all the way, go down. You can practice, go up, okay? Go down. Now you're going to have to put your eyes there. Make sure this iris diagram is at 10, because we'll use 10x first. And make sure this is stage control, which is right in the middle. So we go up, go up, little bit on the top. You can do the place you cannot move. Okay, so right here. Let's talk this one more time. Okay, we go move this up to the place you cannot move in. Put the glass slides in, and then put the iris diagram at 10. Okay, this is the preparation. Then put your eyes there. Then you're gonna go down a little bit, and then you will see a bunch of clear specimen, but you will not see the morphology. So you can come here to see what it looks like. Come here to see. Good to see you again. That's what the 10x looks like. Come here to see. That's what the 10x looks like. Is that correct? Come here to see it again. Have a couple of representatives of the whole classroom. That's what the 10x looks like. Okay, you want to see anything, you want to see the morphology. Okay, so we certainly need the oil. That's what's the oil immersion. And you can do a practice. If you directly go to the 100x, it's very fuzzy because of the light refraction. So what we do, we're going to put oil. So one twisted, that's going to be 40x. We don't use it. One more twisted right here. Now we put the 1 drop of the oil. Make sure this oil is big and huge right in the middle. That has to be a huge drop. Okay. Now go 100x. This will be the challenge. Sometimes it doesn't work very well. Ideally, this only need a very simple adjustments. That's called a parfocal. because we say once the lens focus to use 10x, we switch to 100x, the focus stays with very minimal adjustments, which means you only need to using fine focus. But there is one thing I forgot to do. The iris diagram needs to put at 100x. Otherwise, you see it's very dark. So when I put at 100x, you will see what the specimen looks like. So go on here to see it again. That's underneath the 100x what it looks like. It's more clear, you see the grape shape. Coxail is Staphylococcus aureus. Come here to see it. Either way, either one. That's what happened. That's very clear, the morphology, and the staining, I think, is crystal violet. The purple one right here, can you see it? Okay, so that's what we do. So let's talk about this one more time, okay? Not confusing you. This you can practice, stage up, stage down. By yourself, you won't block it. All the way, first of all, go to the top. Of course, this has to open. And then make sure iris diagram at 10x. And then you put your eyes there, and go down, go down, go down, go down, you find something. Okay, then what you do? You need to put oil. So, one twisted, second twisted, right in the middle, put one drop of the oil, then put 100x. Since it's a parfocal, so only need a very minimal adjustments. And then don't forget the iris diagram has to be put at 100x. Make sure the light amount going through the glass slides is enough. Okay? Then you can use your cell phone to take the picture of what you do the observation. This is the first one. When you finish, using your lens paper, not a paper towel. You should have lens paper is somehow in your personal tray, something like this mesh. That is called a lens paper. Okay, not paper towel, because this is expensive. You use your lens paper to take out of the oil. And since microscope may not be used for a while, you could also use lens paper to clean the lens first. But don't use paper towel, because lens paper is only for the lens. That's very important. Okay? So that's all I have, and go ahead to do the practice. Everybody grab one, then take the rotation, and my PhD student, Royal, will be there to help you if you need help.